So I think we can start. Something happens with my camera. I hope you hear me, but camera just switched off and error with turning it on. But hopefully you hear me, right?
Yes.
Okay, good. So we start our next session, extragalactic astronomy. I will chair this session, and first speaker, Dainis Dravins from Lund Observatory, with talk of initio simultaneous simulations from the wild universe to details in stellar spectra. So please, floor is yours.
Thank you, and nice to joining a meeting at Ventspils, although of course I would have preferred to be back in Ventspils at this time. So let's hope the pandemic ends before long. The topic is about initio simulations. And so if we see this. In physical sciences, much of what is discussed concerns observations or theory, but this will not be about these topics. It will be about something else. It will be ab initio simulations, which by many are seen as a third group of, say, attacking problems in physical sciences. And I'm choosing this topic both because I'm involved in some of these fields myself, but also because it is something that naturally leads to big data, and is something that generally is a topic that is of relevance for universities or institutions which also have departments of high performance computing, especially if such a department has some collaboration with units doing observations and theory. So what I want to describe here are two examples of ab initio simulations. The first one is something where I'm not personally working on, but which has received a lot of, say, interest. And these are large-scale cosmological simulations, where one is basically simulating the evolution of our entire universe. So what is done there? One starts with some sort of, well, input. And the input, in this case, you start with something after the Big Bang. You have matter, you have baryons, you have dark matter, and you add in some random perturbation so that you get some sort of distribution of dark matter, gas density. The gas has a certain temperature and a certain content of higher, more heavier elements. Then basically you add on the physics of the laws of physics, hydrodynamics, what happens under gravity, how does gravity afford things, and you do this stepping forward in time through cosmic history. And as much as is realistically possible, you can add chemical processes, magnetic fields, stars are forming, they are evolving, they are blowing stellar winds, and there were black holes forming and so on. And the output of such simulations is then basically what happens with these parameters over cosmic time. In this case, you start with something as Z, that is the redshift parameter. This is the early universe, up to much more recent times. And for example, matter clumps together, gas becomes denser, so does the gas temperatures, and the chemical composition of the universe changes, especially the metallicity. There's a growth of heavier elements. In this volume, all sorts of structures begin to form. You have stars forming, you have clusters of stars forming, you have galaxies forming, you have black holes forming, and you can follow these things developing from early times here at Z equals 5, all the way to Z equals 0, which is the present time. So you can follow many examples, hundreds, thousands of examples, how things that are becoming galaxies are forming. The amount of data that this produces is significant. It may even appear overwhelming. So these are some examples of the parameters that appear. You have black holes. The number of such black holes that appear, here's the scale, how many are there within this illustrative simulation, which is one of the big ones in this field. There are hundreds or thousands. And the same thing goes if you have, say, nebulae, gas clouds forming, we talk about 100,000, and there are dark matter structures that are reaching, on the order of 1 million. So the amount of data that is produced is huge. And this is sort of the beginning or the earlier ones, and the volumes one is now is treating is like 300 megaparsecs cubed. And the data that is produced by these simulations in this case is available to the public. But what is available is a very large data volume. We're talking about 1 petabyte basically of simulation data. But having that much data also means that you can start searching for rare and unusual objects. And one example of such studies is what started only a few months ago, the search for cosmological jellyfish. Jellyfish. Yes, jellyfish. And the reason is that many galaxies that are simulated, they look like you would think of galaxies. I mean, there are spirals, they're elliptical, they're compact, but then there are galaxies that are very asymmetric. They have long tails, and these long tails contain stars and cosmic gas. Why are they formed this way? Is that a numerical or anomaly? Is that some sort of rare physical phenomenon? This is not known. And how do you find them? Can you use artificial intelligence or something? Well, maybe, but there is nothing quite like the human eye to identify unique shapes. So what is happening is this is being now offered to the general public as part of the Zooniverse project, where the general public can download images, simulated images, and search for weird things like on the bottom line here, which are actual cases in this from this simulation. We have galaxies that look like, well, with some little fantasy, like jellyfish. Now, when you make such a simulation, you are the ruler of the laws of physics. You can change the laws of physics if you want to test something very different. Maybe you want to introduce a different dependence, how gravity changes with distance. If it's not inverse square, it means something different. You can simulate other universes if you believe in the multiverse concept, that if there is another universe, what laws would exist there? For example, you can run this whole simulation and you change something. For example, you remove the weak nuclear force. The weak nuclear force is what causes the radioactive decay of elements. So if you take away that force, you only have 3 fundamental forces, not 4 as we have in our universe. Things become different. You don't get the same nuclear synthesis, but you get evolution, you get stars, you get some sort of not the usual supernovae, but you get something different. And this means that you can do things and see what are the consequences if some law of nature would be slightly different. So this is a big field, and many groups doing this, and it has become possible over the last 10 or 15 years. But let us look at something more local, and this is something where I'm myself personally working on. What about the solar surface, stellar surface, and the spectrum of the stars? If we look at the surface of the sun in high angular resolution, this is taken images or a movie taken with the Swedish Solar Telescope on La Palma, that very island from where there is just now an ongoing volcanic eruption. Images from the Solar Observatory of a few days ago, they show how the plume of volcanic clouds is rising at the horizon, although the observatory itself is not, it's much higher up and some 20 kilometers away. So this is what it looks like. You have the structures evolving. You have convective cells, the granules, the bright ones. They're bright because they're hot. Their gas is rising. Gases cool off, become dark, and then sink down. And some places you have bright elements, and these are basically magnetic regions. This has become possible to numerically simulate since maybe 15 years ago. And these are examples of such simulations. These are synthetic images where you look down on the stellar surface from the top. And this is scale in megameters, thousands of kilometers. And to the left, the bluish false color is a hotter star, 6,500 Kelvin. To the right, on the same horizontal linear scale, is a cool star, 4,000 Kelvin, and you can immediately see the difference. In the hotter star, things are much more vigorous, things must move faster, things must have a higher temperature contrast in order for convection to carry the correspondingly higher energy flow upwards. So this has happened for already quite some time. What is new first publication this year, is that it has become possible to compute also ab initio spectra. In these hydrodynamic simulations we just saw, there you put in gases, you have a simulation volume. At the bottom, you add heat, you add a heat flux, and then you force the gases to follow the laws of physics. Basically, they are absorbing radiation, they are emitting radiation, and they're moving. I mean, you know how many megawatts per square meter they must be transported upward, and you get the boiling of the stellar surface. To get a spectrum from these, you need more input. You need basically a catalog of spectral lines that can be obtained from the laboratory. And in this case, one took basically the whole catalog of stellar spectral lines that is available on various databases, some 600,000 spectral lines throughout the visual to the near infrared. And then you add them, you compute the radiative transfer to these hydrodynamic simulations, and the outcome are then synthetic spectra, but there is no modeling. They're not fitted to anything else. You only start with the temperature of the body, the metallicity. You must assume something of what is the chemical composition, and then you just let it run. So these examples to the left is a cooler star, 4,000 Kelvin. And so this is the wavelength from violet to the red to the infrared. And you have basically the black body curve here that with some deviations. Here's a hump at 1.6 micrometers, which is due to the negative hydrogen ion, which is an important opacity in stellar atmospheres. And if you go to the infrared, you have a lot of absorption bands from molecules. Here to the right, we have a hotter star, almost 7,000 Kelvin, corresponds roughly to the spectral type F3, which is a sharply peaked, Planck radiation curve that peaks in the blue, and we have strong absorptions here, absorption edges due to the hydrogen Balmer lines. There's a Balmer discontinuity here, and of course the thing continues also to the infrared. Now, such data one gets not only for the star as a whole or the center of the star, but you get it from various positions on the stellar disk, because you're computing what is a spectrum in various directions, what goes straight up from the star and what goes sideways. Or put in another way, what do you see from the center of the stellar disk? And when you go to the limb, the flux is lower in your direction and the structure is different. And somewhere here, you can start to appreciate what is the amount of data. The original spectrum from the violet to the infrared is computed with a spectral resolving power of 1 million or more. You have 3 million data points, and then you have 20 points across the disk of the star. And that you have for each of the temporal snapshots of the simulation, roughly 20 snapshots. And that means in total on every star, for every stellar model, you have more than 1 billion data points. And that means even things like spectra of stars are going into the range of big data. So what can one read out of this? Well, for example, these are absorption line profiles with wavelength going left to right and intensity upward. Each time snapshot gives a slightly different line profile, of course, because the stellar surface is dynamic. If you average these line profiles, you get an asymmetric line, and you also get something that changes with time. And that change is something that today is a limiting parameter in detecting small exoplanets, such as another Earth in orbit around another sun. For these detections, one is looking at how the planet or how the star is influenced, how the star is moving around the common center of mass with this exoplanet, and it undergoes a slight Doppler shift towards us or away from us. and how to find other Earth analogs. Today, the limitation is not instrumental. It's not that telescopes are not big enough. It's not that spectrometers are not good enough. It's because stellar variability is much greater than the small perturbation caused by the star. So we need to understand what the star is doing in order to find these planets. And the temporal variability, for example, here to the left in a cool star, 4000 Kelvin, to the right in the solar temperature, the variability is much smaller in the cooler star than in the sun. And if we go to even hotter stars, it is even greater. So by studying such variability as has been simulated, we can try to identify what variability is there in reality. For example, in the true solar spectrum seen as a star. And such telescopes exist in a few places. One is on La Palma. It is a small telescope placed on the outside of a big nighttime telescope, but during daytime, this small telescope is collecting sunlight and obtaining the spectrum, the high resolution spectrum of the sun seen as a star every 5 minutes. And so we can follow what is the apparent radial velocity of the sun over time. And it's jittering. It's jittering a few meters per second continuously in response to the dynamics of the solar atmosphere. And these spectra are now becoming public. There are some 35,000 such spectra, and these are now observations. So also this is something that goes into the realm of big data. And these are things that we and others are working on with the ultimate aim to understand how to find another Earth. So these were some of the points. So thank you for listening.
Uh, thanks a lot. Any questions, comments? So while people thinking, you mentioned this is very interesting possibility to find out our stars or our stars suitable for like similar to sun. Is it right? Is it correct for sentence?
Yes, the possibilities are that you make an ab initio simulation, and then of course actually what comes out of these simulations is something equivalent to a large amount of observational data, because you don't know the results. There is no fitting to anything. So the results may sometimes be surprising, but in hindsight, you can identify a phenomenon. I mean, what did it come from? I mean, and then maybe you can find it observationally. That is one of the strengths of ab initio simulations. You are just letting nature do its thing inside the computer, and then you see what does it come up to. And of course, other stars is one field which we and others are working on. Some things are still quite difficult, like making detailed magnetic field simulations, but things are getting there. And with high performance computing, this is becoming accessible. And actually, some of these hydrodynamic models can be run even on ordinary computers. Well, it will take a few months of execution time, but they can be done if you have a computer just sitting and well, chewing in a corner of the room. After a few months, it will be finished.
Yeah, it's also interesting. Probably like a computer cluster or supercomputer. It's better solution to make such calculations, of course. I see Ivar Schmelt rising hand. Ivar, do you have questions?
Yes, I have two questions. One maybe more technical. It is, you mentioned that you started one of the simulations with Z equal 5. What about initial conditions? How you get them?
Okay, well, of course, one uses the best understanding of what was there, but basically what you do, you introduce just some random field of parameters, and after a rather short time, it has randomized itself. And in some cases, it is even sufficient to have the internal computer inaccuracy. I mean, things will just grow. The same thing is if we simulate, for example, solar surface, that if the volume starts out being wrong, so to speak, it will take a certain time, maybe a long time, but it's a certain time until the program, say, stabilizes itself. It will be equivalent if you would artificially stir the solar surface with some big thing, it will take some time to relax. So ideally, at least, the whole thing stabilizes itself after a while. But you must, of course, if you're not wasting a lot of computing time, you have to make some intelligent guess to begin with.
And the second one maybe is more philosophical, and it is what is your attention to the idea that our universe also is virtual, and we live in virtual matrix.
Okay, well, we have virtual conferences, so what is the next step? Is that a virtual? No, I don't think I have an opinion on this, but of course, at some point you can start asking where is the, I mean, if you would imagine, well, you can ask the question how detailed a simulation is sensible. If we would have a hypothetical super duper computer that would simulate every single piece of, for example, the sun, that would reproduce the sun in some sense, but we would not get any more wiser, because in order to get wisdom or understanding, I mean, there must be some sort of, I don't know, rationalization or simplification. But in this specific case of your question, I don't have any. I think it's very speculative, but it's an interesting philosophical question.
Okay, thank you. Thank you. However, if it's true, then we know nothing about the scales in the universe of the creature.
Yeah, thanks a lot. And it's a really interesting question in virtual conference. Are we virtual at all or not?